So this is from question 2, that's from question 3 on our worksheet. Let's try it together. This is all we have, and we have to sketch the graph of y is equal to x. So from what we know, we're going to have our axis. I don't know where the y will be for now. These points lie on it. 0, 2, that's the y-intercept. 2, 0, that's the x-intercept. Oopsie. So if we have that, 2, 0, when x is 2, y is 0. So it's going to pass through here. When x is 0, y is 2, it's going to pass through here. Okay? Then our C is x is equal to 4, y is negative 2. So it's going to pass through somewhere here. Okay? That's what we know. Then we can look at this. Clearly, let's consider the gradient. So between 0 from negative infinity up to 4 is going to be coming down. The gradient is negative. Okay? And also, do you mind? Do you mind? And also from here is going to be positive gradient. Okay? We also know that there's a change somewhere here. At 0, according to the second derivative, at 0 we have a point of inflection because there's a change in the shape of the curve. Okay? So this being positive tells us the gradient was increasing up to this point. Alright? And this tells us the gradient was reducing. So when the gradient, the rate of change of the gradient is negative, it means it was positive, then it's moving towards negative. Is that not? So there's a curvature, point of inflection at x is equal to 0, which is here. But then there's a positive change in the gradient, means even though we have a negative gradient, it's beginning to go to positive. So it means it's coming down. All right? Don't forget the fact that if you have that of a point A greater than or equal to 0, do we have increasing or decreasing? Come on. I wrote 2 facts yesterday. Concave up, down. This is going to be the minimum, right? So it's a concave up. This is maximum, concave down. Is that not? So if you notice, at this point, where your second derivative is positive, which is this one, so it's coming down at that point, right? It's coming down. So it's a concave up shape. So anywhere before here is coming down like that, isn't it? Then here, where you have that is going up. Is it? Okay, so where do we have that? Between 0 and 2. Between 0 and 2, we have a change in the shape of the curve. So it could be something like this, coming down. Then from here, this shape begins. Are you with that? Are you with me? So this shape begin doesn't mean it goes like that. We have to be careful. Because if that is the case, it means we have a positive gradient here, which we don't clearly. We still have a negative gradient. So definitely, while it's going like this, after I get to this point, the gradient is still negative, so it's still going down. So basically, it's not just the entire shape. It's just part of that. So because there's a change here, that is why you have a point of inflection there. There's a change in this shape. These two shapes are combined here. Half of this and half of that.
The left side be like this.
Wait, what? Oh, yeah. Sorry. You get my point?
No, as in the two things you drew. Should it be like this instead?
Okay, let's look at it again. Positive. We have this. Oh,
Yeah.
sorry, my bad. Okay, half of this and half of that. Do you understand that? So that is a stationary point of inflection. Is it? Okay, no, it's not a stationary point of inflection either, because at this point, your gradient is not 0. Can you see? At this point, the gradient is not 0. At that same 0, which is the point of inflection, I thought that would be a stationary point of inflection. Okay? In that case, no, No, this is negative, negative. That's what I'm saying. So it keeps going down. So we're supposed to say that if that point we have is 0, there's no turning point there. We don't have to have that stationary point, even though there's a point of inflection. We've done that in one of the questions where the dy by dx equals 0 has no solution. But then we investigated the point of inflection. Do you remember that? There's a function with exponential, whatever, whatever. No. The function with 2x squared minus 6 over x squared. We tried to find any stationary point and we couldn't solve that point, that question. It was in the room 212. Remember the first question I solved on Saturday? So it's possible you don't have a stationary point, but you still have a point of inflection. I think that is the same case we're having now. Am I making sense? Anyway, so we're going to have a curve that goes like that. So it's coming like that. Then this is going like that. Something like this. Wait, what? This one? Oh, the other way around again. Sorry. So it should go like this? Is that what you're saying?
Yeah.
Okay. So it should go like this. Then it should go like that. Right? So after this, what do we know? Is there a turning point? At the turning point, dy dx is 0. So 4 gives a turning point. At this 4, this is positive because you can see anything after 2, second derivative is positive. If the second derivative is positive, you're having this shape. So that point 4, which is here, is a minimum point. Okay? So 4 is the turning point because this is 0, negative 0, positive, right? So 4 is a stationary point, and it is also a minimum point because the second derivative there is positive. So it's going to turn here. And x is equal to 4 is when y is equal to 2. So it's going to turn here. Something like that. Is that what you got? For those that have tried it. It continues. Karen, are you lost? Because we have to go. Like I have to quickly do this because of our time. This is all we know. This is the graph of the derivative. We're trying to draw the graph of the function. So what do we know? When the derivative is equal to 0, you have this. And that should be the stationary point. But at f prime of x, f prime of minus 3 is equal to 0, and f prime of 1 is equal to 0, implies that what? Minus 3 and x is equal to minus 3 and x is equal to 1 are stationary points. Agree? So whether the stationary point is a turning point or a point of inflection, we don't know yet. But we know they are stationary points. Okay, so for you to get point of inflection, f prime prime must be 0, right? Do we have any information on that? Yes, we do. Because remember, at x is equal to 1, there exists a Okay, at x is equal to 1, the gradients of that curve is equal to 0. Can you see? At x is equal to 1, the tangent will be horizontal. Okay? So the derivative of that is what? Can you see that? If you had to find the gradient at x is equal to 1, you would have drawn a tangent, right? So your gradient will have been 0. So because this one is the turning point of this happens. And this simply means this. So this point is actually a point of inflection to the original function. Does that make sense? So we have established that these 2 points are stationary points, and now we have a proof that this is a point of inflection. Does that make sense? But it's not just a point of inflection, but a stationary point of inflection. So it's not a point of inflection that comes down like that. It's a point of inflection, it's a point of inflection that looks like this, sort of. Okay? Not a normal point of inflection where this changes and we're talking about this one. No, this is a non-stationary point of inflection. Anyway, quickly. So what do we know? We know there's a turning point here. So let's try to draw the sign diagram, if that helps. So from -3, there's nothing happening at x is equal to 0. There's something happening at x is equal to 1. So what happens between -3 to the left, the gradient is positive, is what? F prime, this is F prime, right? So F prime is positive. Can you see? This picture you are seeing is for the gradient function. Okay? The gradient function is above the y-axis, so the gradient is positive. Between here and here, the gradient is negative because it's below. Also, from here to here is also negative. Right? So let's see if that helps to picture the curve. So definitely there's a change. Where? There's a change here.
Yes.
Right? So this indeed is a turning point. So gradient was positive, then gradient was negative. Gradient was positive, then gradient negative. So it's indeed a maximum point. Alright? So there's a maximum point at this point, x is equal to 3. Okay? So the curve must have come like that. Are you with me? But do we know anything about the intersection of the curve itself? We don't. We don't, right? We don't. Okay, so fine. But we know this is a point of inflection, but a non-stationary point of inflection. Give me more clue if I've missed something out quickly. Sorry, I'm rushing because of the time. I'm not sure if I pick everything necessary to be picked.
The other turning point.
Say that again?
The turning point between -3 and 1. Is that another point of inflection?
There's another turning point here. True, yes. There's a turning point here. The turning point of your f prime of x. At this point, we don't know what that is. So let's call that some x1. At x1, okay, at x1, the derivative of that is equal to 0. Isn't it? At x1. So that means this is equal to 0. So that's a point of inflection. Right? But that point of inflection is not a stationary point of, is it? A stationary point of inflection? Yes. Because if you find the gradient here, which is a stationary point of inflection, so there exists a stationary, wait, is
No,
it?
it's not.
Yes.
Because that's the graph of f prime.
Yeah, but if you find the tangent,
No,
oh, that's not the graph of f.
This is f prime.
So what is the gradient at this point?
The gradient is 0, but the value is not 0. Because it's not stationary. This is the graph of f prime.
There exists a non-stationary. Sorry.
Oh, because it's
It's not f.
Do you agree?
sorry.
Because even though this happens, this is not 0. Even though this happens, okay, because this is for x1, right? But this is non-zero. How do you know this is non-zero? It doesn't cross the x-axis. That's not where it crosses the x-axis. This is where it crosses the x-axis. It doesn't cross the x-axis here. So it's a non-stationary point of inflection. What does that tell us? So it's the one that comes that way. So this is where the shape of the curve changes sign at this point. So let's see. If it's coming this way, it turns here. At this point, the shape of the curve will change sign. Then it's going to, what do we know about this point? It's a stationary point of inflection. What does that mean? It's a point of inflection where another sign changes, isn't it? Hello, talk to me. Point of inflection is where the sign changes, so you have something like this, or you could have something like that. This is a non-stationary point of inflection, but this is a stationary point of inflection, something like that. Understand? So this one is here, right? But does it come down or up? Can we try to draw the graph of the second derivative? I hope we all don't get into trouble for not going to stretching. let's try to find something about the second derivative. Minus 3, point x1, and point 1. Okay, so on this side, what do we know about the second derivative? That is the gradient of the gradient function. So looking at the curve of that, what is the gradient up to this point? Right? What is the gradient between here and here? Still negative, positive, right? And negative. This should help us making the last decision. So we can see clearly there's a point of inflection here, right? And so if we have, let's talk about the curvature now. At this point, where's our turning point? What are the turning points? The turning point are these two, right?
Yeah.
At minus 3, you have negative, so there's a maximum there. That has been established. Hello? At 1, what's going on?
I think it just goes like that. You go up.
Do we have enough information already?
Yes. Like you just go up and then you just.
So we know this will come like that. There's a change here. So it's coming down. Then it's going to turn.
No, it might just. It might just turn. Like it doesn't cross the x-axis until 1.
Wait, it's not, doesn't cross x-axis?
I don't know, but if you.
F,
yeah, I think so.
F of x
I think.
at
inflection.
this point is not 0. Why?
I mean, it crosses when the x is equal to 1. So that you have the.
Maybe not
It
necessarily.
doesn't have to.
So if there's a change in the shape of the curve here, we don't have any information to say it crosses, it comes down between these two
It
ranges.
just has to be like that.
No,
So it has to be like this.
but because after 1 is negative, so it has to
Look,
go down.
look. From 1, before 1, this is positive, yeah? And after it is negative. So we have here, within this range, do we have increasing or decreasing function? Hello? When you have this, yes?
Yes.
Yeah.
And when you have this, right?
Yes.
So if you have a point, what kind of point of inflection do we have at 1?
Non-stationary.
No, it's
Stationary?
Stationary.
Okay, so basically at this point you are having something, part of this one, like this, like that, right? So in that case, maybe I can move this up a little bit. So if I have a turning, so then the other half starts from here, right? Then what kind of turning point do we have at 1 again?
Stationary.
Stationary. I don't have enough distance. So there will be a turning point here. After 1, what happens to the curve? What kind of shape? This shape?
Yeah.
So but we don't know if it's going to come down or if it is going to be up. That's what we don't know. So it's possible you have 2 options. So you have 2 options where the shape of the curve changes like this. This is not high enough. Something like this, and then it changes this way. Where there's a turn in here. Or it could be like this. It's coming that way. The changes could be, unless we have any additional information, we would never know. Do you understand my point? We know up to this point. We know this is stationary where the curve changes sign, but we don't have enough information to know if it is above this point or below this point, unless I'm missing something. Okay? Look through this again. Let's discuss on Thursday. Okay, I don't mind if we have to go through another question, but look through this again. Let's discuss on Thursday. The other worksheet that I intend to give you, I won't give you today again. Too bad. We're spending so much time because we don't have time. Look, I've taken 15 minutes of your break time. Stretching is over. I'm sure you're happy.
Masha.
Peter? Questions? You want me to go through it again? Anyone? No? Yes? Karen, talk.
Yes.
Okay, quickly. From what you know, the black one, which is the graph of the gradient function, crosses x-axis as these 2 points. So definitely, if this is equal to 0, then these are stationary points, clearly. But the stationary point, are they normal stationary point or point of inflection? We don't know. Are they turning point or point of inflection? Clearly, this gives us a turning point eventually. This gives us a point of inflection. So we don't know which one. Now, at x is equal to 1, we notice that there's a turning point, there's a stationary point based on this function, right? You can see clearly, because that is where, I'm not talking about the fact that it turns now. I'm talking about, I'm not talking about the fact that it crosses the x-axis now. I'm talking about the fact that there is a turn here. So even the gradient function has a stationary point here. Apart from the gradient function intersecting x-axis. Intersecting the x-axis is what gives us this. When a function is equal to 0, it means that's where it crosses the x-axis. But we are interpreting this as a stationary point because by what we know, dy by dx is equal to 0 at the turning point of the original function f. If the first derivative is equal to 0, then you have a turning point of the original function. So the function we are trying to draw has stationary point at -3 and 1. Understand? But if you look at the gradient function graph, it has its own turning point. This is establishing the turning point of f. But this is telling us the gradient function also has a turning point. If the gradient function has a turning point, then this happens. If the original function has a turning point, the original function is y. So we say dy by dx is equal to 0. If this something dx is equal to 0, that something has a turning point. Or stationary point, if we may put it that way. So dx of the f prime of x having this 0 implies that this function itself has a turning point. As you can see, it turns here, that's why we can write it. But what is the ddx of the first derivative? That's actually this one. So if the second derivative is 0, then you have a point of inflection. So it is been established now that even though this is a stationary point, we don't know, but we have established that at this point, it's not just a stationary point, it's a stationary point of inflection.
Then why isn't the point of inflection on x equals 1?
No, that is it. This is where it changes.
Oh, the y.
It's coming from the concave up, it changes to concave down at this point. The only thing is we don't have enough information to establish if the change of the curve is established at the upper part or at the lower part. That's why we have two options now. Unless we are given some point on the graph, like the first question has given us rightly. Oh, this point lie on the graph. Unless we have that third information or that additional information, we will never know. So if somebody decides to sketch it in the red one, somebody decides to go the blue route, for this information provided, both would be acceptable.
So it wouldn't be on the same point as the f prime x?
If anybody wants to leave, please feel free to. Okay? Yes?
It wouldn't be on the same point as the f prime x?
What won't be the same
Wouldn't
one?
the point of inflection be on the same point as...
Yeah, that is it, you see? X is equal to 1, x is equal to 1, depending on which curve. That's why I make sure the change occurs here.
So it wouldn't be on the same y value?
It won't be on the same y value. That's what we don't know.
Why is that?
Why is negative here, why is positive here? Because we don't have that information. Okay? That's the only missing link now. Every other information has been used. And these are the line sign diagram for the second derivative and for the first derivative, not for the function itself. If we have the sign diagram for the first derivative, then we'll be able to conclude. Suppose in addition to all this information, you have something for f of x, and you could see that, oh, from here we have positive. Then clearly, it's this one. Or you have, oh, negative. Then clearly it's the blue one. But we don't have that information. Does this make sense, everyone? It's kind of ambiguous case, sort of. Okay? I think I saw something in your book that says something like, oh, you can have different options too.
Yeah.
So it's possible you have different options. But make sure you exhaust all the possibility before you conclude that, okay, this is my own option. But do not do two options in your solution. Just focus on one, unless the question say, draw the possible graphs. Okay? But I will not expect any ambiguous case. Your question will have been solved, checked by experts, and be concluded that okay, student will not be confused before it is given to you. It shouldn't be up to this. It shouldn't be this tough. Okay? Thank you.